Okay, so it's a couple of minutes past 4. I guess we can start. In case you have trouble hearing me or seeing the slides, just write something to the chat. I can then try to fix it. And if you have any questions during the presentation, I think there's a delay of about 4 or 5 seconds, like that. But if you have any questions, then just ask it in the YouTube chat. I'll keep an eye on it, and then I can also answer it. Okay, so today's topic is called Advanced Differential Attacks, and as the name suggests, we will hear something more about classical differential attacks, or something which can be done with them, some in an advanced method. So essentially we will first start with something that is very similar to what last week's lecture was about, and then we will see how we can do things differently, such that in some cases the attacks get more efficient. But it's all differential, it's just some additional techniques, so to say. Okay, so let's start with a short outline. So first there will be a recap. So what is differential cryptanalysis and what is the AES block cipher? And the reason is that we will use the AES block cipher in some of the attack methods today. And then after this short recap section, we will talk about truncated characteristics and truncated differentials. And first we will focus on a toy cipher, so on a very simple example, and then we will focus on the AES. And truncated differentials, or truncated characteristics initially, they will play the largest role of today's lecture, and there we can immediately see how we can improve differential attacks by just applying an additional technique, or an additional twist, so to say. Then after the truncated differentials, we will talk about impossible differentials, which are, well, actually similar, but we will talk about that in the context of a Feistel network, of a very simple Feistel network, and again in the context of AES. And after that, towards the end of the lecture, we will talk about the boomerang attack, which essentially is a combination of some of the differential techniques. And we will then talk about the square attack on the AES. This is somewhat different than a classical differential approach, and we will need some new notations for that, but you will see here. So basically, we'll first talk about the attacks on toy ciphers, always, and then about the application on the AES. And what we will also talk about actually is why the AES is secure against differential attacks. So they did something very clever, which makes it resistant against this. Okay, so let's start with a recap. So differential cryptanalysis, this is now the general topic, is now approximately 30 years old. And essentially it's a very powerful method, traditional, but also still today on some very specific schemes. And the idea of differential cryptanalysis is to deduce information about the secret key. So in the best case, you would like to recover the secret key. And it does so by essentially tracing differences through pairs of plaintexts and doing the encryption or the decryption, but actually this can also be applied to things that don't do encryptions. For instance, it can be applied to hash function also. This is then called rebound attacks, which partially use differentials also. So essentially the idea is, the very basic idea is to basically we have an input difference, some difference, and then we get with some probability an output difference, and based on that we try to recover something. We try to recover some information about the key, for instance. And there's a difference between a characteristic and a differential. So for an R-round characteristic here, we essentially trace the differences through each of the rounds. But for an R-round differential, we don't really care about the middle rounds, but all we really care about is essentially the input difference, so delta 0 in that case, and the output difference. So that's the difference between a characteristic and a differential, and this will also be a difference later when we talk about truncated characteristics or truncated differentials. And we will see then also why truncated stuff can be better in some cases. Okay, so this is the very general idea about differential cryptanalysis. You should have already heard about it in last week's lecture. So let's continue with a very basic approach of a differential attack. So usually we try to find some, for example, some good differential characteristic. And in this example, this very simple example here, the characteristic, so that we have some probability for the characteristic over 3 rounds. And essentially what we do is we extend this by 1 round, but we do some, in the best case, some partial key guess for the last round in backwards direction. And what we try to do here is we try to just verify if the characteristic, if the differential holds. Okay, this is what we do in a classical way. And for a correct key, so basically if our guess is correct, then we have some probability, namely the probability we already know before, so this can be computed. But if the key is not correct, then usually it holds with the very generic probability of 2 to the minus n, where minus n, is the block size in bits of this thing here. So this is still very, very basic all, and so it's quite evident from this description that for the attack to work, we need that this probability here, such that an input difference delta 0 maps to an output difference delta 3, this probability needs to be higher than 2 to the power of minus n. So in the best case, it's much higher, so we can make the attack efficient. So that's what we try to achieve, and as an attacker, of course, that is what we try to achieve and what we try to have. Okay, so that's still very, very basic, nothing new about that. And what we will talk about now is how we can actually get security against this attack vector. And what we will focus on here, later on a Feist network, but here mainly on an SPN round function. So SPN stands for substitution permutation network. And such a permutation is usually consists of many rounds, and each of these rounds has in the beginning some substitution layer, so this is nonlinear, and then some affine transformation. This is the mixing layer, for example, also called. And we will try to see how can we actually design this so that we get security against this attack, and what is actually responsible for the security. So we want to defend against this differential attack. So of course, if we recall the probability before, that we need this probability to be much higher than 2 to the power of minus n, then of course as a designer we want to keep that probability as low as possible. And actually we want to keep every such probability as low as possible. However, there's a problem with that, namely it's very difficult to compute the probability. So it's possible if we have a very, very small block size. So for instance, for an S box alone, it's very easy, or for any permutation where the block size is very low, it's easy to compute by just brute forcing it. But in essence, if we have a larger block size, which is the case for most block ciphers, for example, then this is very difficult to compute. And what we do instead is we use some bounds. And we will see later a certain number which essentially gives such a bound. And this can very, very nicely be used in order to get some protection against this attack. Okay, but for this bound here, so we need this bound, we'll talk later about that, we have two main properties. And the first such property is, of course, we want that the probability, the maximum differential probability of the S box we use is as low as possible. And then we have that number of the property of the number of active S boxes for each round. And of course, we want that to be as high as possible. We'll see later why this actually is the case. Okay, but these are the two properties now. So that basically the maximum differential probability for the S box and the number of active S boxes for each round. An active S box in that case means, so an S box is active if the input is, so if the input difference is non-zero. So then the S box is called active. Okay, so that already leads us to a design goal, namely we want to have S boxes which have this low maximum differential probability, and we want linear layers or affine layers which result in many, many active S boxes. So that's what we want to have as a designer. So how can we do this for this single substitution permutation network round? Well, we saw that we have these S boxes in the beginning, and then we have this linear layer here. And what is relevant is the number of active components, the number of active S boxes in the input, and of course the maximum differential probability of each of these S boxes. And now if you only consider that for a single round, so we don't consider the mixing transformation, nothing, only a single round, then if we assume a permutation, then we have a bound of at least one active S box per round. So this is actually the minimum number of active S boxes we can have. And why is this true? Well, if we enter with some difference, and if we consider a permutation, then the two different plaintexts won't be the same after a single round. So there must be some difference somewhere. So at least in one S box after this single round, we again have a difference. And again, we have the difference after the second round, and so on. So the minimum is essentially that we have at least one active S box per round. But now if you think about it, if you have a very small S box, like for instance 4 bits or even 8 bits, and we have one active S box per round, so we use this bound essentially, then we may need many rounds in order to achieve the differential, so in order to achieve security against the differential attack. So that's usually not what we would like to use here. Okay, so that's about a single round. And this actually leads to a design goal where we try to design large S boxes, because if the size of this S box is larger, for example 16, 32 bits and so on, then the maximum differential probability can be kept lower, and we need fewer rounds in order to get some security. And this actually has been many years ago the idea that this is actually a good thing to do. Now we do it a bit differently, because instead of only considering a single round, what we can do as a designer is we can consider 2 consecutive rounds. And it turns out that for 2 consecutive rounds, we can do something which is a bit which is more clever, so to say. Okay, here the relevant information is not the number of active S boxes in the input of this first round, because we also have the second round. So what is also relevant is the number of active S boxes in the output here, because that immediately translates to the number of active S boxes in the input to the second round. So that's the idea here. And this number, so the number of active output S boxes based on the number of active input S boxes, this number depends on the linear layer. And this is now the design goal, so we try to find a linear layer which basically gives us a very good bound. And it turns out that there's this metric which is called the branch number, and the branch number actually gives us the minimum number of active S boxes over 2 consecutive rounds. And this is something we can actually use to increase the number of S boxes. So this is what we try to do as a designer. And yeah, so this is some additional information, so it's not so important for the purpose of this presentation, but essentially the branch number can be at most 1 plus the total number of components. So the best case is if we activate one input word here, we have all output words being active. So that's the best case we would like to have over 2 consecutive rounds. And so the new design goal, instead of essentially designing S boxes which are very large, or the more modern design goal, is to design a linear layer instead, which maximizes this branch number. And it turns out that there actually exist linear layers which do that, and they're called MDS matrices, for maximum distance separable. This comes from coding also, from codes. And essentially this is a linear transformational matrix which maximizes this branch number. So basically which makes this branch number 1 plus the number of components we have here. So this is what we would like to have as a designer. Not always, of course, because this is quite expensive to do, but it gives us the best security, so to say. And now let me come to the AES again. So let's recap about the AES, and we will see how the AES actually does this. Well, you should already notice the AES is an iterated block cipher. It has some possible key sizes, some possible number of rounds, and a state of 16 bytes. And the round function essentially consists of 4 steps. We first do this substitution layer, the sub bytes, then the shift rows, then the mix columns matrix, and then we add the round key. So this is essentially how the AES round works. And now let us go over these steps and show why the AES gives us good security against differential attacks with the properties we have heard about now. Well, first we can take a look at the subbytes layer, and here for each of the 16 bytes, the same substitution box is used. And this substitution box, if we go through the maximum differential probability, we can build, for instance, the DDT and read out this value. We see, and this should also be, so this should have been appeared also in last week's lecture, we see that this probability is actually 2 to the power of minus 6. So this is essentially the maximum differential probability for one single S box. So if I have any non-zero input difference, and then I go over all possible values and then also possible output differences, this is the maximum probability for such a translation, so to say, in all possible translations. Okay, so then we have the shift rows. This doesn't really do a lot with the differences, so we will just skip this. It's not so important here. We will see later that in some other things it may be important. And then we have this important mixed columns matrix. And this is actually such an MDS matrix, which has a branch number of 5, because it's a 4 times 4 matrix, so it works on four words here on each column. And it turns out that if we have such a branch number of 5, then if we have, so essentially this matrix can be translated together with shift rows to a 16 times 16 matrix. And then if we do this for 2 rounds, we have exactly, at least 5 active words, because that's the branch number of the matrix, or 5 active S boxes. And if we do that for 4 rounds, we essentially square this, and we get 5 times 5, which is 25 active S boxes over 4 rounds. But now we know that the AES uses more than 4 rounds, so we can essentially iterate that computation, and we can achieve a provable bound even, and say that that the probability of this 4-round characteristic, so focusing only on 4 rounds, we know that at least 25 S boxes are active. We know that the maximum differential probability for each S box is 2 to the power of minus 6. So we can essentially compute that and achieve a maximum differential probability of 2 to the power of minus 150. But of course, this is now even lower than the generic probability, which depends on the total block size. So essentially what we achieve is the maximum of those two. So we achieve exactly that, given an input difference to the AES, any input difference, after 4 rounds of the AES, we can say that each output difference has a probability of maximal 2 to the power of minus 128. And well, that's exactly what we want to achieve by the AES. And that's why the AES actually provides security against differential attacks. So are there any questions to that? Okay, then let's continue. I think, yeah. So let's continue with the new content now, truncated differential cryptanalysis, and we will see now how these differences, so how we can approach it a bit differently, and how we can make attacks more efficient, differential attacks. Okay, so it was first published also approximately 30 years ago. And it's essentially a generalization of the classical differential cryptanalysis. But the main idea, or the main difference, is that we leave parts of the difference unspecified. So we essentially don't care about parts of the differences. Which means that in the end we ignore some bits. For example, if we talk about a bit-based scheme, we ignore some bits, which allows more differences. And the main goal is, and this is also achieved, is that we increase the total probability of a differential, for example. And yeah, an example would be if we enter with this input difference here and we get this output difference here. So in the output, we don't care about the positions, or also in the input, we don't care about the positions of this bit here and this bit. We don't care about the value of this bit, and this bit. But what we do care about is that there are zeros at these positions. So this is only an example. We will see later in more detail how that works. And yeah, this is very powerful against word or byte oriented ciphers. Okay, so let's continue again with a very simple example. We have a toy cipher, and now it's not important to remember what the S box does here. It's just for the sake of completeness here, and the same for the bit permutation. So in the slides now, you have to trust me that what I tell you about the differences or what the probabilities here is actually true. But yeah, so not so important. But essentially, we have a very simple cipher. We have 4 S boxes in each round. We have 4-bit S boxes with a 16-bit block size. And after each of the S boxes, we have essentially this bit permutation, which can also be represented by this thing here. And yeah, and we do this for a couple of rounds. It's actually similar to, for example, present. Okay, so let us first say that this is very now classical differential cryptanalysis, nothing truncated yet. So we can say that a one-round characteristic for this toy cipher thing, namely the characteristic that this input difference maps this output difference, has a probability of 6/16. And now again, you just have to trust me, but essentially, if I build the difference distribution table of this S box, and then together with the bit permutation, I can see the output differences when we focus on this S box here. Basically, this 0 here, this 2 here at the third position means that we have a 2 in this third S box. So essentially, we have 0, 0, 1, 0 as the value. We will also see this later in more detail. But yeah, if we focus on this difference, so we have this input difference, we apply one round, and we have that output difference. Then if we do the math with the probabilities, we find out that this holds with a probability of 6/16. So this is essentially it. And so what we can do now, because we have multiple rounds, right? So what we can do now is we can focus, for example, on 4 rounds, not only on 1 round. And if we focus on 4 rounds and we say, well, we want to have this specific difference not in the beginning and at the end, but we want it to have in the middle also, then what we would need is not only one such translation, but 4 such translations here. So we would essentially take this probability and compute it to the power 4, and we end up with approximately 80/4000. So there's nothing truncated about that yet. This is still classical. And what we can also say, and this is already a hint, maybe what we can do to improve it here, we can focus on the differential rather than the characteristic. And if you remember, in the differential, we don't really care about the middle values, but only the input and the output here. So what we can do is we can say, well, we want to have an input of this difference, we want to have an output difference of that here. And we don't care what happens here. So essentially, there may be more combinations which lead exactly from that input difference to that output difference. And there are indeed more combinations, and therefore this differential holds with a probability of 4 times that. So 300/4000 approximately. So this is already much better. We have basically a 4 times probability. But again, there's nothing truncated about the difference yet. So this is a very specific input difference and a very specific output difference. So how can we improve that? And as I said, if you have any questions, just ask it. I'll keep an eye on the chat. Okay, so how can we improve that? Well, we can try to improve it with this truncated characteristic. And essentially what we do here first is we focus again on this input difference, 0020, and if we do the computations and if we try out what is actually possible after 1 round, then we can see that the possible output differences, if we enter with this input difference here, are this one, this one, this one, and this one. So there are 4 possible output differences. And now here it's with bits, so it's a bit more clear. So essentially 0020 is 0, 0, 0010, 0. So this is 2. So this is the input to the permutation. And now we can do the same with these 4 output differences here. We can translate it to the bit level here. Okay, and then we can simply compute the probability of the probabilities of those, and we see that essentially we have a probability of 3/8 for this output, for this very specific output difference after 1 round, and we have a probability, so the same probability for this output difference, and we have a slightly lower probability for these two, for each of these 2 differences. But essentially these are the 4 possible output differences. And what we can actually see is, well, but for each of these, and this is all of the possibilities we have, we don't have any more output possibilities. For each of these we have, for example, zeros here. So the first 2 bits are always 0, then the second word, so to say, the second nibble is always 0 also. Then we have these 2 bits which are always 0, this single column of bits is always 0, and so on. So what we actually have is we don't know this column here, because it can either be 0 or 1. It's with a higher probability 0 than 1, but we don't know. And the same here, which has essentially the same probability, and the same also with this column here. And this now already leads us to the idea of actually, well, why do we actually care about these values? Why don't we just focus on the values we actually know about, these zeros here? And that's essentially what truncated is in this truncated characteristic. And this is essentially it. So instead of specifying this column here with either 0 or 1, we'll just give it a symbol. And in this case, it's star. So it doesn't really matter what symbol this is. It's just to say that we don't care about the difference in this specific position. It can be either 0 or 1. Maybe it's 0 with a higher probability, for example, in that case, but we don't really care. But what we do care about are the bits which we know. For example, these zeros here. And if we do that here, now the same. We take the same specific input difference and we say that after 1 round, no matter what happens, this is the output. So we don't know the positions here, the bits here, here, and here, but we know that the rest are zeros, as can be computed. Then we know that this translation here actually holds with a 100% probability. So not anymore 3/8, 1/8, but actually 100%. And for example, we can also say that we omit the star here, so we specifically want to have a 0 here. Then essentially with these 2 stars, we reach either this specific, so the first specific output difference, or the second one, and we just add now the probabilities of these 2, which is 3 plus 3/8, which is 6/8. So this is the core idea of truncated differential, truncated differentials. There was a question in the chat, how is the differential characteristic calculated in practice? Yeah, we will see also later. So in practice, it's actually not so easy, as it's also the case with the real with the normal classical differential characteristics. So it's not so easy in practice, but there is a lot of trying, and there are also other approaches, like for instance some solving approaches that can compute it over a number of rounds. But yeah, this is something which is not so easy actually. Okay. Okay, so let's continue from that. So now we have a single round, so now let's add another round to that. And again, this is something you have to trust me now. You have to trust me on now. So if we add another round, essentially what we do is we get more uncertainty. So we get more of these stars, but we still know some of the positions with 100% certainty. So these zeros. And equivalently, so if we now start from the situation after the first round, where we have only 3 stars, then we know that this difference here, no matter what it is specifically, so it doesn't really matter what it is, after 1 round leads to this truncated difference, where we don't care about these positions where we have stars, but we just know that there are zeros here. And if we now basically combine everything here, we know that if we enter with this very specific input difference, this 0, 0, 2, 0, which we had in the beginning, we know with 100% probability that after 2 rounds, we will have this truncated difference here. And this is the core idea, because now we have something that holds with a probability of 1, whereas with a classical differential, we would have a probability which is already much, much lower than 1, of course. So that's the idea. Okay, so a bit of terminology, and this makes also clear why the truncated differential actually has a larger probability, so intuitively. So characteristics and differentials are actually not the same. So for example, a differential characteristic predicts the difference in a pair of texts after each round of the encryption. So we really want to know the specific difference after each of the rounds. And this is now different to this differential, which essentially in a differential, we don't really care about the middle differences, which means that essentially a differential is a collection of characteristics. So it actually maps or contains implicitly many different characteristics. And we can also go further here. So a truncated characteristic predicts not only the whole difference in a pair of texts, but only a part of the difference, but again after each encryption round. And this means that a truncated characteristic is also a collection of potentially multiple characteristics. And now the final definition is essentially this truncated differential, which is a collection of truncated characteristics. They are a collection of simple characteristics. So essentially, intuitively, this makes it also a bit more clear why a truncated differential has such a large probability, because it essentially collects many different combinations and possibilities in order to have this truncated difference in the end. So that's the idea. Okay, so now we have this three-round differential. Actually, we had the two-round differential, I think. So this is again something you have to trust me now about. So if we do this for 3 rounds, we end up with this truncated differential characteristic, where we actually define with this truncated difference. So where we essentially have 0 bits at each second position of the S boxes and more stars, more uncertainty. So this is the case after 3 rounds. If we do the same thing we did before, essentially again. But okay, now we have this 3-round differential. So what do we do with 4 rounds? So how can we attack 4 rounds? And this is also similar to what you've already heard about. So essentially what we do is we guess the last key partially, and then we try to verify if this differential actually holds. So that's how the key recovery attacks on 4 rounds works. And well, how does this work in more detail? We consider a pair of texts which has exactly this 0, 0 to 0 input difference. Okay, so this is what we had in the beginning. Then we partially guess the last key k. So this is basically the last key. We partially guess it. And then what we do essentially for the plain texts we have, we request the ciphertexts. We get it from the oracle, from the encryption oracle. And then we partially decrypt each of the ciphertexts we get with this key, which we guessed. And then here we essentially know that this differential here holds with a probability 1. So if this doesn't hold with the guessed key, we know that the key is wrong. So this is essentially the idea how to recover the key. And now you may ask, well, but what does partial guessing actually mean? So why is this better than just guessing the key? Well, it's here important that it's not necessary to guess the entire last key, but it's actually enough if we just guess 4 bits of the key, because this is sufficient for the decryption of 1 round to the corresponding S box in order to verify that we have the zeros here, or we don't have them, and then we just discard the key. So that's the idea. We can essentially guess 4 key bits independent of the others. So that's what makes the attack possible. So are there any questions to that? I will wait a couple of seconds. Okay, then let's continue. We can actually also do this for 5 rounds. It's not so important to understand the concept of truncated differential, but I just explained very briefly. So we have this single 3-round truncated differential. How can we do it now how can we apply the key recovery attack on 5 rounds? Well, what we can do is, instead of only guessing the last key, we can try to guess both some bits of the first key and also of the last key. And now we can ask ourselves the question, how many pairs actually lead to this difference here after the first round? So essentially we start with our 3-round differential after the first round. So we have to somehow cover the first round. That's the idea here. So that's why this question here is. And it turns out that there are exactly 8 distinct pairs which actually map to this difference here. And now the idea is basically that we consider these pairs, we don't know them exactly, and we guess we guess 4 bits of the first key in order to have some candidate plaintexts which actually fulfill this difference we want after one round. And what we do now, well, if we have this, essentially we repeat the same as before. We go to the, we request the ciphertext essentially, then we guess the last key, and again we see if, we check if this holds or it doesn't hold, and if it doesn't hold this relation, so these zeros here essentially, then again we are able to filter wrongly guessed keys. So again, this is very similar, but just instead of starting at the beginning, we start after the first round, and we now have to guess the first parts here in order to basically cover the first round in order to start after the first round. So that's the small difference here. Okay, so I think this were the 2 attacks. Yeah, good. So now again, as a small recap, and now considering 5 rounds, we have truncated differential and classical differential. So what's the difference? Well, in a classical differential attack, we also need to partially guess the key, and we need to use, for example, this differential here, which holds with a probability of approximately 80 over 1000. This was this 300 over 4000 before, which is the same as 80 over 1000 approximately, so it's actually the same. So this is in a classical differential attack, but in a truncated differential attack, what we can do is we partially guess a bit more, but this holds with a probability much higher than that, so namely exactly 1. So we can immediately do this step. So this is essentially the difference. And that's also why in some cases truncated, so these are actually better in order to recover something we want to recover. Okay, and again, this is not only applicable to things like key guessing or things like block cipher. So this was a block cipher approach here, but this also applies to like other statistical approaches. This also applies to things like hash functions and so on. So this is actually quite wide, the area. Okay, so this was truncated differential on some toy cipher. What can we say about the AES? So this is now a concrete cipher. Well, for the AES, we had before, first we need some definition here. So yeah, so essentially we call the first diagonal here the main diagonal, which is red, and the second diagonal is blue, and the third is here green, and the fourth is here black. So that's just for some notation. But even without these notations, it will be clear what is meant later. And yeah, these are the anti-diagonals, but again, it's not so important to remember. But what is important is that we can build something like before, so this truncated differential, also for the AES, and specifically we can do it for 2 rounds of the AES, and we can do it with a probability of 1. And we here omit the final mixed columns, which is reasonable. It's also omitted in full round versions, so the final mixed columns. Okay, and how does this work? Well, in the AES, for example, if we enter with some difference here, and we let these differences here 0, we enter with some difference here, we know that it's now some other difference here, but what we don't know, at least not with 100% probability, we don't know the actual difference this step. So assuming a key before, of course. We don't know it, but what we know is that there is some difference. And what we also know is that the shift rows doesn't change where the difference is, because it basically does nothing for the first row. And we know that the mixed columns now basically spans this difference now into the first column. Again, we don't know the precise differences, but we know that there is some difference. And we know that there's not some, so there isn't any difference in the other bytes, in the white bytes here. So the difference here is 0. Okay, now the at round key operation comes with doesn't change the differences, and more specifically doesn't change the position of the differences. And now we do the same again, we do sub bytes, which again doesn't change the position of the differences. And now we have the shift rows, which does change the position now, because we have differences also in the last 3 rows. But we know how it changes them. And we have at round key then in this 2-round version again at the end, which again does not change the position of the differences. So what we know is, and this is truncated approach here, we don't know the difference here, we don't know the difference here, we don't know it here, and we don't know it here, the precise difference. But we know that there may be some difference here, and more importantly, we know that there's no difference in the white bytes here. And this is the same essentially what we had before with these 0 bits, for which we knew that there is a 0 difference at this position. So this is what the truncated differential is of 2-round AES. And of course, we can build a secret key distinguisher with that difference. And the secret key distinguisher is essentially something where we try to distinguish between some ciphertext or some plaintext, depends on which direction we go, which was generated by the construction we try to attack, or which was generated by some pseudo-random permutation. So if we can distinguish these two, that's actually a bad property for the construction we want to attack. So the goal from the designer is that basically it's impossible to distinguish between a certain construction and a pseudo-random construction. And so symmetric key ciphers must be immune to this attack. And for 2-round AES at least, it's clearly not immune, since we can easily distinguish if we have only 2 pairs, and if we enter with such a difference here, with doesn't really matter which difference, we know for AES at least that after 2 rounds we have zeros here with a probability of 1. So this is exactly the same as 2 slides before this truncated differential. We know that for AES, after 2 rounds, there are zeros at this these positions, while for a random permutation, the probability that all these byte values are 0 is of course 2 to the power of minus 8, so that's the probability of a single byte value being 0 to the power of 12, because we have 12 zeros here, so 16 minus 4. This is 2 to the minus power of minus 96, which is much lower than 1, which means that we can easily distinguish with only one plaintext ciphertext pair with high probability 2-round AES from some other pseudo-random permutation. And what we can also do is we can also extend this to 3-round AES essentially. First I will skip it here, but essentially what this does is it doesn't hold now with a larger probability, but essentially we have a probability of at least 99% that we can do this also for 3 rounds. So yeah, but it's essentially the same as before, where essentially we try to distinguish the 3-round AES construction from a pseudo-random permutation. It's very, very similar. Okay, so this was about truncated differentials. Now about impossible differentials, but first I will again wait a couple of seconds if there are any questions. Okay, then let's continue with impossible differentials. And so there's now a distinction. Usually, as an attacker, we try to have some differential, or which holds with a relatively high probability, because that makes an attack more efficient. However, also if we have some differential which holds with an exceptionally low probability, and now it's almost always 0 because exceptionally low is the generic probability already. So if we have a differential which holds with 0 probability, this can also be exploited in an attack. And if we actually have such a differential which has a probability of 0, so this means essentially it cannot occur for this scheme, then this is called an impossible differential. And the idea is essentially that we combine two such differentials, two differentials which have a probability 1, so that they have some contradiction in the middle, so they conflict when they essentially meet together. And we will also see this here in our approach, so I will go through this step by step. So assume that we have a Feistel network, so this is essentially a two-branch Feistel scheme here. And let us say that f is injective, okay, which means that it's injective. And now assume that there is some differential, for example, this one, which maps, so delta 0, which maps to 0 delta here, over 5 rounds. And now it follows, sorry, I didn't do this now. Okay, this is maybe easier. So let's say we enter with some difference here, which is here this delta here. And essentially what we have now at this position here, at the L2 position, is the same position, the same difference. Sorry, why? Well, because we have difference 0 here, so this doesn't get changed. Here it's the input to this function, but it doesn't get changed either. And essentially we arrive at this position with exactly the difference we had here at the input. So this is the idea here. And let us for now ignore this red dashed line, and we'll see later why this is important. Okay, so this red normal line here is the same difference everywhere. Okay, but we say that we also we know that this maps to 0 delta essentially over 5 rounds, so we know that there's some difference also at the end, right? And this is essentially this part here, and let us assume that's also so that's the same difference by this definition here. So we basically have some difference here. We can go backwards since this is here 0, this doesn't get changed. So we have the same here. Here it's the input, but it doesn't get changed. And now it goes up there, and now we're here. And essentially here we have the same difference we had below here. Okay, so this is now the setup, so to say. And we say that there is the differential where this difference is essentially the same as this difference. Okay, but now we can take a closer look at that and say, well, we know that the difference at R2, hence this difference here, is non-zero. Why is it non-zero? Well, because we enter with a non-zero difference, it gets added to this 0 difference. So the difference we get here, we don't know it exactly, but it's non-zero. It can't be, it's non-zero because f is injective. Okay, that's the reason this red dashed line here. But if this difference here is non-zero, so the difference we have here, then we know that essentially the difference after applying f on this difference here, so we basically apply f on this difference, so in this R2 and with the third round key, we also know that the output difference, since again f is injective, is non-zero. So we have a non-zero difference here. Okay. So what this means is that we have a difference of delta. This is from the definition from the beginning. We have a difference from delta here, which is again a non-zero difference here after the XOR here. And we know that this is the same by definition as the L2 difference plus this difference, which is the output of the f function, because this is the x, so this is by the construction essentially. But we also know that this difference here, so basically this times this, is not equal to the difference L2, because essentially we arrive at a contradiction here. But we know or we want to have, that this L2 is exactly delta. This is by definition of the beginning. So what they end up with is that delta is not equal to delta, which is clearly a contradiction. So we can conclude that essentially this differential that we basically enter with delta 0 and we leave the 5-round permutation with 0 delta as differences, this is impossible. So the probability of this differential is 0. This is the core idea of an impossible differential. Okay? So again, why does this work? Well, we have that the output difference here is the input here plus the output of f, which is exactly this. Okay? But since the output of f is non-zero, we have that this plus this cannot be equal to the same again. But this is delta by definition, and delta is not equal to delta, and then we have this contradiction. Okay? So this is now an impossible differential over 5 rounds. We can actually also attack now 6 rounds, well, with a key recovery attack. And the idea is essentially to encrypt pairs of texts which have exactly this input difference delta 0, then to guess the last key, decrypt the ciphertext, and if the output difference is 0 delta, then we know that the key guess was wrong, because after 5 rounds this input difference cannot lead to this output difference. So this is the approach here. Okay, are there any questions to that, to the impossible differential? Okay, then let's move on. Well, this was again an example of an impossible differential attack on a very on a Feistel scheme here, but this can also be done for the 4-round AES this time, not only 2 rounds. And again, it's tracing differences. So we had already this from the first example, where we have where we arrived at this output basically after 2 rounds. We omitted the last mixed columns. Now we add it. Okay, we add the last mixed columns. We know that the differences here get split essentially. So we have potentially the whole block is active, so to say. So we can't do any. We have complete uncertainty, so to say. At round key operation doesn't change this. We are still active everywhere. Okay, so now let's just leave it that way, and let's consider the backwards direction of 2 rounds. If we start with this difference, where we know that at round key didn't change anything, the same. So shift rows essentially changes it such that we have this represent. We had this before shift rows, so the inverse of shift rows actually goes from this to this. We know that subbytes does not change the positions of the differences. The same is true also for the round keys. We know that mixed columns operates on columns only, so this remains inactive, so to say. We have these unknown bytes again. Shift rows shifts these 0 different bytes to different positions. And subbytes again does not change the positions, so doesn't change the positions of the non-active bytes, of the active bytes. So what we arrive here now, if we basically combine this is that we have a probability of 1 to arrive at this representation after starting with 1 single active byte. And we also have a probability of 1 if we basically go into the backward direction of 2 rounds AES, and we start with this representation of active bytes, essentially with 12 active bytes and 4 constant bytes. And what we achieve is that after the 2 forward rounds, we have this representation, and after the 2 backwards rounds, we have this representation. This is clearly not the same, especially the value, the positions, of the constant bytes, of the 0 differences. So this is again a contradiction, and we can conclude that we can build an impossible differential here also for the AES if we go into both directions. Yeah. So this is essentially the same like before. Again, in text, so if we have a pair of plain text which differs in only one byte at the beginning, then basically it cannot be equal in all the 4 bytes of any of the 4 anti-diagonals. So this is the impossibility result essentially here. We cannot arrive at this representation if we start from the beginning. And again, this is the same as for the Feist approach. We had one difference which goes in the forwards direction, another trait which goes in the backwards direction, and we have some contradiction in the middle. And so we conclude essentially that the whole mapping over the 4 rounds in that case is not possible. So this is the same as before. And yeah, we can set up a secret key distinguisher. Why can we do so? Well, because this the case that this actually holds, that actually we have these 4 bytes which are non-active also here, because here we don't know it. It may be true that we have this representation, but the probability is very low because we have 4 bytes and the probability is so 2 to the 32 to the power of 32, sorry, due to the bytes here. So essentially the probability of the matching is very, very low and for a normal permutation. But for an AES, we know that the probability is 0 because it cannot occur. This is then how we build the distinguisher. Of course, it's not a 100% probability distinguisher, so we need some pairs. But then if we have so many pairs, it's sufficient to distinguish the 2 cases. So to basically decide whether these 4 rounds apply to the AES or if it's just some pseudo-random permutation. Okay, and as before, this can also be extended to an attack on 5 rounds. So it's essentially an attack which exploits the impossible differential for 4 rounds, and similar to before, it actually eliminates wrong round keys if this doesn't hold. And how does this work? Well, in a bit more detail. So we start with some intermediate values T1 and T2. So these are values for which this 4-round impossible, for which we can apply this 4-round impossible differential mapping. So these are values which differ by only 1 byte in the beginning. And basically what we do with these bytes here, we make a key guess in the backwards direction, and by this key guess, we arrive at some candidate plaintexts. Okay, so this may not be true, but we arrive at some candidates. And what we do is, with this plaintext, we just send this to the oracle, and we receive this C1, C2 if the oracle gets us this essentially. And what we do now, we just check if the impossible differential is fulfilled or not. So if this mapping actually holds or not. And well, if it doesn't hold, then we can basically conclude that the key was not correct. So I'm again waiting a couple of seconds. Okay, yeah, okay, I've told you about that already now. Yeah, so you ask for the encryptions, and then basically if this happens, if the impossible differential happens, which we don't want to happen, which is impossible, then the partially guessed key is not correct. So this is, I actually told you that already. Okay, so this is all about truncated differentials and impossible differentials. What we will talk about now are 2 additional attack vectors. So one is the boomerang attack and one is the saturation attack. So the boomerang attack is another type of differential attack. So it was first introduced around 20 years ago, and the general idea is, well, if we have some trail, so for instance a differential which covers the whole cipher but which has a very low probability, maybe we can somehow split it in 2 differentials for two parts of the block cipher, for example, and then combined they have maybe a higher probability. So that's the idea of the boomerang attack. And as the name suggests, we will in some way go down and then back up again. And we'll see this also on an example here. So okay, so what's the procedure? We first have two plaintexts again. So for example, P and some P star, which is essentially P plus a difference. And we encrypt these two P's. So here. We encrypt these two P's, and what we arrive at is C and C star. So we split the cipher or the block cipher in two parts. So the first part is this E1K and the second part is this E2K. But of course, if we send something to the encryption oracle, it will give us the final encrypted value. It will not give us some intermediate value here. It will always give us the final value. So okay, we let encrypt these plaintexts here. We then compute, we arrive at C and C star. Then we introduce another difference here. We compute basically D and D star. And what we do now is we go into the backwards direction. So this is where the name boomerang comes from. And essentially we decrypt D and D star, which are now ciphertexts again. So we do this here, and again, the one part of the, so this is the second part of the decryption, the first part of the decryption. So again, we split it into two parts. And what we arrive at is this Q and Q star. And what we do now is we just check if the difference between Q and Q star is this alpha. And so this is what we do. So we don't really care about these differences here. So we don't compute them, so to say. But what we do is we compute these values. We just get the encrypted values C and C star. We add a difference to get two new values. We use them. We let them decrypt essentially, and we arrive at two values Q and Q star. And we check if the difference here is actually the same. So this may sound very complicated now, at least it may sound like we have to rely on more differences or more probabilities. So in total, the probability may be much lower. But actually, this is not the case, because if we analyze this, then we have following probabilities. Well, we have first the probability that alpha, so this is this alpha here essentially, the difference here, the probability that alpha goes to beta, which is the probability after the first part of the cipher. Okay, so let us say that this probability is P. I have it also here. Okay, then what we also have, and we need to rely on, so we fix the probability delta. If you remember, we fix it. So this is chosen by us. So what we need to rely on, or what we need to get essentially to compute, is the probability that this delta maps to gamma after this first part of decryption. So this is the second probability we need, and let us say it's Q. And finally, what we need is that the beta we achieve here, so yeah, we achieve here, essentially maps to the alpha probability again. And let us say that's P prime. And now in total, the probability that essentially the output here, the final output, the Q XOR Q star is the same as the original input probability, is equal to this probability times this squared. Okay, this makes sense, squared, because essentially this needs to match, here and here, here and here. So this squared times that, because we go that way, times the probability times P prime. And now the idea is that if this product here is sufficiently large, then it can be used in an attack. So this is the general idea of this attack. And what we want to have, if we apply this attack, of course, is that this probability here, which essentially gives us the efficiency of the attack, that this probability here is larger than the probability of a truncated differential, which we would use just to go into one direction, for example. So this is what we want to have. And if this is the case, then we can use this boomerang approach where we essentially go first down, so into the encryption direction, and then we go back up to the through the decryption direction. So this is essentially the boomerang attack. And now this may seem very theoretical, but actually it has been used in this way. So for example, against the file cipher coconut, this was actually broken by using this boomerang attack. So it's essentially a chosen plaintext attack, adaptively chosen ciphertext. Why adaptively chosen ciphertext? Well, because we get out some ciphertext, we actually modify the ciphertext, and then based on this modification, we ask the decryption oracle to get us new plaintexts. So that's why this adaptive here. And essentially it's the combination of two shorter high probability differentials in an attack on the whole block cipher or the whole scheme. And there are multiple variants of it, and one is even from last year, so this retracing variant. Okay, so this was the boomerang attack, and we will now go to the last topic of this lecture, which is integral attacks. This is again some kind of differential attacks. It's a bit it's a bit different compared to the attacks so far. So we need some new notation, some minor notation, but it's not you will see it's actually quite intuitive what this actually does. Okay, so integral attacks. First, they were called the square attack, and later names are, for instance, SA, SES, so also saturation attacks. They're still called that way. And typically, it works very well on ciphers which are word-oriented. And that's also maybe we can connect this word saturation because we try to saturate something, and we will also see this later what we try to saturate actually. And yeah, for this presentation, we will focus on the AES, and we will see here a couple of possible attacks or distinguishers. Okay, but first let us define this set here. So this set we enter with is essentially, for the AES, a set of 256 16-byte texts. What this means in a sense is that we have 256 plaintexts. Okay, this is some set here. And of these 16-byte plaintexts or texts, every one of these 16 bytes can be described by one of the following notations. So it's either constant, which means that the byte is the same for all of the 256 plaintexts. So for example, it's 0x10 for all the 256 plaintexts at a certain position, so then we call it C. Or we can describe it by A, which means active, and this means that essentially all the values in all the 256 plaintexts are pairwise distinct, which means that basically each of the possible 256 values occurs in this byte. So for example, we have 1, 2, 3, 4, 5 in this byte up to 255. So this would be active then, but of course it doesn't need to be in that order, it can also be mixed, but each value occurs. And then we have this balanced notation, which can also define a byte. And balanced essentially only means that the sum in this byte position, the sum over all of these plaintexts is 0. So when does this happen? It happens since we have a characteristic 2 here. So essentially if we XOR the same value to itself, then we have 0. So it essentially means that so an active set is balanced, of course. A constant set is also balanced. Balanced may also be something like that we have some values double or 4 times or 6 times and so on, so an even number of times, but not always the same values. So essentially this is what balanced means, just this property here. Okay, so for example, we can denote the AES state by these letters here, where the first byte is active, so each of the values occurs in the 256 texts, and all the other 15 bytes are constant, so they are always the same value for each of the 256 texts. So that's the idea. Okay, so now let us see what the AES transformations actually do with this set. Where we know that the shift rows doesn't change the properties of the bytes, but just the positions of the bytes, so the indices of the properties. What we know is for the subbytes that the active bytes remain active. What does this mean? It means that if I have one byte which assumes every of the 256 possible values in all of the 256 plaintexts, then if I apply the subbytes transformation operation, then it's the same byte, or all the bytes which are active again. And this is true because subbytes, because the S box is a permutation. So this is true therefore. Okay, what does it do to constant bytes? Well, if we enter 256 times with the same value, then the output may be some other value, but it's still the same for all of the plaintexts, so they remain constant. However, if I enter with a balanced byte, then the output becomes or gets undetermined. So we don't know anymore what this actually is. Okay, so this is what subbytes does. Sorry. So what about at round key? Well, in at round key, the active bytes remain active, so it doesn't change anything. And the same for the constant bytes, and also the same for the balanced bytes. So nothing changes here. Okay, what does mixed columns actually do? Mixed columns, so constant bytes remain constant. You can simply check this also by applying it on a column. We know that a single active byte, we actually also had this before, gets essentially spanned over the column, over the first column, or over the respective column. So all the bytes get active. So this is actually an interesting property. And what is also interesting is that for balanced bytes, they remain also balanced. So that's just the transformation, what it does to the status here. And this is also so if we have 4 active bytes, then the output is actually that we have 4 balanced bytes for the mixed columns operation. And you can easily check this, and this holds. Okay, so what does this mean for the AES then? Well, we are interested in a 3-round distinguisher now. So we essentially want to have we essentially want to distinguish 3 rounds of the AES, or the output after 3 rounds of the AES, from the output of some other pseudo-random permutation. So how do we do this? Well, we start again with this familiar representation where we have the active byte. So this assumes all possible values and some constant bytes. It doesn't matter what the values here are, but they're the same for all of the 256 ciphertexts. So we actually do these operations, we apply these operations now to all of the 256 plaintexts. Okay, we know that that subbytes essentially doesn't change anything about the status here. We know that shift rows, especially if we have here only the first row different, doesn't change anything either. We know that mixed columns essentially spans the differences here to all the 4 bytes in the first column. And now we know that these don't change anything. However, shift rows changes the positions here again of these active bytes. So this remains the same, but shift rows changes the positions. So now we have these mixed columns. And what happens now? Well, now something more happens, because we have A also in these columns here, not only in the first one. So what happens is that everything gets active. Not only the first column, as we have it here, but every column here. Okay, we can now simply continue. We know that the ground keys doesn't change anything, subbytes doesn't change anything. Now shift rows doesn't change anything either, because we have everything active, so it changes the positions, but everything is the same. And now we can think about, well, now everything is active, so what does mixed columns actually do? And we had this before for the mixed columns operation, where it actually changes active bytes to balanced ones in the columns. and this is precisely what happens. So essentially, we get the 4 columns here balanced. And what does balanced mean? Again, it means that if I sum over all of the values, over all of the 256 values at the first position, the output is 0. Okay? And the same is true for the second byte, the third byte, the fourth byte, and so on. The same is true for all of the bytes, which means that if I actually sum all of the 256 ciphertexts here in that case, then the output will actually be 0. Okay, this is what the status here tells me. And yeah, we have a round key at the end, but this doesn't change anything. So what do we have now? Well, we have that if we use such a set of 256 pairs, plaintext ciphertext pairs, we actually request the ciphertexts from the oracle. And in the plaintext, we have 1 byte active, but each of the values is actually of the 1 byte because we have it well active, and the other 15 are constant. Then we can say that if we have the AES, so more specifically 3-round AES, then the sum of the ciphertext we receive is equal to 0 with probability of 1, because we know basically that this mapping here holds. We sum all of these 256 ciphertexts, and the probability is 1 that we have a sum of 0. And what is the probability for random permutation? Well, it happens only in 1 out of these block size cases. So we have a probability of 2 to the power of minus 128. At least if we focus on a 128-bit block size, as is the case for the AES. So what we can do now is we can distinguish 3-round AES based on this property here. So this is the idea of this saturation attack or integral attack. And again, this representation may seem similar to what we do in this truncated differential approach, but it's a bit different in that we use 256 texts here, really. Okay, and now we can essentially attack 4 rounds. How do we do this? Well, so remember, this distinguisher goes over 3 rounds, so it doesn't give us a distinguisher over 4 rounds, but a 3-round distinguisher, is actually exactly what we want in order to attack 4 rounds. And how this works is very simple. So we omit again the final mixed columns. This is reasonable. It's also done in practice. And what we do now is we just guess the last key here, the last round key here. We basically decrypt back. So with our guess, we can decrypt this single byte. And now we just compute the sum over all 256 intermediate values we have here. And if this property holds, so if this byte is still balanced, then then with a very high probability, the key guess was correct. And if it doesn't hold, then with a probability, so with high probability, the key guess was wrong, because the probability, so the guess holds, the property holds for an incorrect guess. The property holds with this probability here. So if it holds, then with very high probability we have found the right key, and if it doesn't hold, then we can discard the key immediately. So that's the idea of the attack. Are there any questions to that? We are nearly at the end now. Okay, then let's continue with the final adjustment here to this attack. So what we can do now, of course, if we have an attack on 4 rounds, in the case of the AES at least, we can in this case, we can very easily extend it to 5 rounds. But this means that we have this mixed columns matrix here at the end of the 4th round, which we hadn't before, right? We didn't have it here, now we have it. Which means that in the very last of these 5 rounds, so the 5th round, essentially, we need to guess 4 key byte values in order to achieve actually this representation here where we need to guess one value. So in total, we need to guess 5 key bytes in order to verify this property, which means that now we have, of course, we need around 5 times 8, because 8 is the 8 bits for each of the elements. We need around 2 to the 5 times 8, which is 2 to the power 40 steps. But essentially, it's exactly the same attack as before, just we need more guesses here in order to basically undo the mixed columns operation here, which we didn't have before. So actually, yeah. Okay, so as a summary, so these were the attacks actually. As a summary, there are many variants of statistical attacks on block ciphers. We heard about standard differential attacks in last week's lecture, but there is actually more to that. So there are, for example, these truncated differential attacks or these impossible differential attacks, which we've heard about today. And there are also higher order differential attacks actually, and we will hear about that. I think in some of the next lectures, in the algebraic cryptanalysis lecture. And yeah, there's also the boomerang attack and the integrity attack, which we've heard about today. And what is also important maybe is that these techniques can also sometimes be combined in order to achieve a more efficient attack. And also important, so I've only talked about block ciphers today, so about keyed constructions. And these attacks cannot only be applied to block ciphers, but also to unkeyed constructions. So there are variations of statistical attacks, of differential attacks, also truncated attacks that can be applied, for example, to hash functions. For example, there's this rebound attack, which also uses differences. So yeah, that's the summary, essentially. And yeah, these are some questions you should be able to answer now after this lecture. And otherwise, thanks for your attendance. Yeah. And if you have any questions about the lecture, I will stay here for a couple of minutes still, so you can ask any questions in the YouTube chat. And yeah, otherwise, thanks and have a nice evening.